So my name's Ran. I'm a launch coordination engineer here. So years back in college, I met this guy called Ling, and we used to hang out at somebody else's lab and talk about everything under the sun, from geopolitics to history to whatever. He went a different way. He was doing physics. I did computer science, and then 10 years passed, and we got back together again. And it turns out he's been playing with photons in the lab, and I got curious. I said, "Well, tell me about it." But since you're going to tell me about it, why don't you tell these other guys at Google too? I'm sure they'd be interested. So here we go.
Okay, thanks for coming and thanks, Vandev. Okay, I'm an experimentalist in quantum optics in the National University of Singapore. Okay, and what I do in the lab is I create something called entangled pairs of photons. Can you hear me? Yeah. Okay, right. And it turns out that these pairs of photons can be used for something called quantum key distribution. It's sometimes called quantum cryptography. Okay. And what I'm going to do today is I'll give you guys an introductory talk about what quantum cryptography is and how it can be implemented and what are the possible ways you can try and compromise the security of quantum cryptography. Okay, so this is just a basic overview of my talk. Okay, so I'll just begin with what's cryptography, what are the encryption keys. You guys probably know that much better than I do. What I'll try and introduce is what can quantum cryptography do, which is different from classical cryptography. Then I'll talk about the BB84 implementation, which is a very standard way of implementing quantum key distribution nowadays. There are commercial companies which are willing to sell you products, okay, based on this BB84 protocol. And then I'll try and explain how the BB84 protocol can be implemented and what are some of the ways you can try and hack the system. And then I'll try and end with something on how quantum key distribution can be implemented using more fundamental, more fundamental physics ideas. So let's go on. Okay, so the whole idea actually started back for secure communication started back in the 70s when a guy called Stephen Weissner, he thought about how you can try and encode polarization states of photons inside money, so you can make money that cannot be copied. Okay, now, but then the whole field actually took off only in 1984 when two guys called Bennett and Prasad came up with a way to distribute encryption keys for quantum, encryption keys in a way that cannot be hacked based on the principles of physics. So let's have an overview first of what secure communication usually is. Okay, there are two ways to do it. Okay, there's symmetric encryption methods, and then there are the asymmetric methods. Okay, in the symmetric methods, you can have the one-time pad, okay, or the Vernon cipher, or you can have something like 3DES or AES. Okay, what happens is that Alice and Bob on both sides, they share a key. Okay, they share two keys which are the same. And what Alice does, if she wants to send a message to Bob, she runs a message through the key. Okay, and what happens is you get a random string of bits which can be sent to an secure channel. And once Bob receives that random string of bits, he decrypts it using his key, which is the same, and he gets the message that Alice wants. Now, the other way to do it is using RSA or elliptical curves. And what happens is that Bob has two keys. He keeps one, which is his private key, okay? And there's a public key which he sends to Alice, and Alice can use it for encrypting her message, and she sends it to Bob. Now, what is wrong with RSA? Well, there's nothing really wrong with it, except that the security of this asymmetric method of encryption is based on the difficulty or the perceived difficulty of factorizing numbers. So what happens is that if you take dedicated hardware, okay, or you find some clever algorithm, or you can have a quantum computer, and then you take some time with it, and then you can finally extract the key. So the security of the communication can be compromised in some ways. Now, so the problem is this. If you want really secure methods, then you probably want to try to use symmetric encryption methods, okay? And then that means that Alice and Bob must have the same encryption key. Okay, so how are Alice and Bob going to get the same encryption key? And that is the problem that quantum cryptography tries to solve. Okay, actually, I don't like the name quantum cryptography because you don't in this thing we are talking about, you don't try and encrypt any message. The only thing you're trying to do is distribute an encryption key between two parties. So I prefer the name quantum key distribution. Okay, so to do key distribution, there are two ways. Alice can make her encryption key and give it to a trusted courier who'll bring it over to Bob. Okay, or Alice and Bob can try and obtain the keys in some kind of tamper-safe devices. Okay, now it turns out that you can use the principles of physics to encode the key either in the form of a trusted courier or in the form of tamper-safe devices. Okay, so I'll walk you guys through this. Now, that's a quick reminder of what is a good key. Okay, so a bad key is of course something which is always the same, and a better key is something which looks slightly more random. Okay, so now it turns out that again, using the principles of physics, you can get pretty random outcomes which can form your random key. Okay, so how do we do this? Okay, first of all, we have to understand that information is physical, and it's encoded inside into physical objects. Okay, so if Alice wants to encode her random key and give it to Bob, she can, encode it either in holes in paper or with ink. Okay, in a classical way, and then she can have a piece of paper with holes inside, and then she sends it over to Bob. Bob can read when there's a hole is 0 and where there's no hole is 1. But these are what we call based on classical physics. These are classical objects, okay? And basically they can be copied. What we want to try and find is for a way to encode the information into physical objects that cannot be copied. Or when the copying is done, the copying leaves a trace. Okay, so what we try to do is we try to use quantum particles as the courier for the information. Okay, so the idea is basically that if you can encode the key into quantum particles, and these quantum particles cannot be copied perfectly or cloned perfectly, okay, then the measurements and the copying will actually disturb the state of these quantum particles, okay? And what happens is that when Bob tries to read out the state of the quantum particles, he finds that the state that he expects is not the same as what Alice would have sent to him, okay? And so the eavesdropping effort actually leaves traces, and this is how the information of the eavesdropper is revealed. Okay, so one way to do this is to encrypt the key inside the polarization state of single photons. Okay, so let's see how it's done with single photons. Now, you can think of photons as, photons are simply the smallest indivisible packet of electromagnetic energy. And electromagnetic energy can be viewed as a wave. So now, the polarization state of a photon can be viewed as whether the electromagnetic wave is vibrating vertically or whether it's vibrating horizontally. Okay? So what you can do is say, when I send a photon in the vertical polarization state, when it's vibrating vertically, I will encode a 0 bit. Okay? And when it's vibrating horizontally, I will encode a 1 bit. Now, how do you read out the information of zeros and ones when it's based on photon polarization? Is you send the photon into something called a polarizing beam splitter, and it sorts out photons which are vertically polarized or horizontally polarized. So in that way, you actually detect photons which are carrying the 0 bit or the 1 bit. Okay? Now, the key point is this. If an eavesdropper tries to do this, and she puts detectors after the polarizing beam splitters, she detects the photon in the particular polarization state, but then the thing is you can only detect the polarization, detect a photon once. Once it's detected, it's destroyed, okay? So keep that in mind, because it turns out that for quantum key distribution, what you do is this. You don't encode your 0 and 1s only in the vertical and horizontal polarization states. You can also encode, or you should also encode, your 0 and 1s in the plus and minus 45-degree polarization states. So basically, you think that the horizontal and vertical polarization states look like this. What you do is you rotate everything by 45 degrees, okay? And you can also encode 0 in this state and 1 in this state. Okay? So basically, what you should employ is you should employ 2 ways to encode your 0s and 1s. Okay? Now, why is this secure? It's secure because when you measure the polarization state of photons in the same basis, you always get the same outcome. So for example, you look at the figure at the top. You have a photon in the vertical polarization state coming in, and it hits the polarizing beam splitter. It leaves the polarizing beam splitter, it's transmitted, but when it sees a second polarizing beam splitter, it's still transmitted. So what we say is that the photon polarization states, when they are measured in the same basis, okay, they always the states are preserved. The outcomes are always the same. But what happens is, if you send a polarization in the plus 45-degree state, okay, when it hits a polarizing beam splitter which measures in the horizontal and vertical basis, there's a 50-50 chance that it's either transmitted or reflected. Okay. Now the thing is, after it's been transmitted and reflected, okay, for example, look at the green photon which comes in, hits the PBS, and then it's transmitted. Now this transmitted part, if it hits the second PBS, is transmitted again. There's no longer a 50-50 chance of being transmitted or reflected, because what you have done is you projected the state of the photon in the 45 into the vertical. Okay, that's what we mean when we say that an attempt to measure the polarization state of the photon actually changes it. Okay, now if the photon is originally in a vertical state, therefore you don't disturb anything if you measure in the same basis. But the polarization was in a state which is different from the state that you choose to measure. Okay, then you have disturbed the state. So you can see in this way what we mean by a disturbance on the polarization state when you are trying to measure it. Now this point is actually kind of important, okay, of how the whole QKD scheme works. So if you have any questions right now, I can take some questions. Yes?
Actually, the chances for 45, or let's say the X degree deviation from the vertical, this means that you have to calibrate your detectors very well, and if the detector is just some minutes or seconds deviated, this means that you have one chance to lose some detection, right?
Okay. I don't quite understand the question because it's very long, but let me try and see whether I understood it completely. You are saying that it's very important to get the polarization state measurement correct.
Yeah, because every deviation will increase your chances to read a random
Yes, that's right. Okay. Yeah. So he's right. Okay. The question was, is it important to get the polarization measurement states are really correct? Yes, you have to get it correct, because when you have to make sure that when you're measuring HV or you're measuring plus minus 45, okay, it's important to get those states correct. But it's not so crucial in it, because if you're working on photons, okay, there are optical elements which are actually very high quality, which give you exactly HV or plus minus 45. Yeah. Okay, actually, in this talk, if you guys have any questions along the way while I'm showing the slides, just stop me at any time, because sometimes I do fly along a bit fast. Okay. Okay, so let's go back to how we encode information. Now, I was saying that you can encode zeros and ones in either the vertical or the horizontal polarization states, but you can also encode the zeros and ones in the minus and the plus 45-degree polarization states, okay? So you have two ways of encoding your information. And how this whole QKD system works is that you prepare your single photons in the states which you see up here. Okay? You prepare the single photons in this polarization state, or this one, or this one. And then what Alice does is she sends all these single photons over to Bob. Okay? And then Bob must make a random choice, okay, of measuring either in this basis or in this basis. Okay? Now what happens is that if Bob chooses photons to measure in this basis, when Alice sends him this, okay, then there's a 50-50 chance that he gets either the horizontal outcome or the vertical outcome. Okay? In those cases, Bob and Alice cannot make any sense of the measured photons. They cannot really communicate anything because there's a 50-50 chance. But if Alice actually sent this states and Bob measured in the same polarization states, then they're always correlated. Okay? And in those correlations, from those correlations, Alice and Bob can build up a random encryption key. So basically in quantum key distribution, half the time you can get correlations for a key, and half the time you can't. Okay, so this is actually what I was describing just now is actually called the BB84 protocol. So it's also called a prepare and measure protocol, because what Alice has to do is she has to prepare the polarization states of her single photons, okay, and then she has to send it across to Bob, and then Bob has to measure the polarization states. So what happens is, you see here is that you have your single photon source, you pass it to some optical elements, okay? The optical elements are here, okay? So this will decide which polarization state it is, whether horizontal or vertical. This element will actually decide whether you want to maintain the HP or you want to rotate into the plus minus 45. Okay, thanks.
No problem.
Okay, then what happens is the single photons are now in some state which Alice knows. Okay, then she sends it across to Bob. Okay, and then what Bob does is Bob has to choose again which polarization states to measure in. So when you see the dices up there, okay, that means that you need a random choice. Okay, so at every step here and here, you need a source of random number generators, okay, to make the choice. And what happens is after you have done, Bob has done the measurement of the polarization states, they do classical communication. This can be an open channel. It doesn't have to be secure, where they discuss. So Alice will say, okay, for the first and the second photons I sent to you, they were in the horizontal and vertical basis. And then what Bob would say, okay, first and second I measure in horizontal and vertical. So they agree to keep the measurements that they did for the first and second photons. But if they in the discussion, they find that the polarization states that Alice sent was not measured in the same state that Bob did, then they would just discard those photons. And in that way, they discard 50% of their keys, and 50% actually remains for the encryption key. Now, of course, in any practical implementation, there are errors, okay? And so what happens is that the next step is that there's error correction and privacy amplification. Now, privacy amplification simply means that you must assume that all the errors in your key that you have, okay, come from an eavesdropping attempt. Okay, so what you do is you use the error fraction to estimate the information of an eavesdropper. And once you know the information of the eavesdropper, you can try and correct actually suppress all the information that she has. And that step is called privacy amplification. Now, this is an example of how a practical BB84 system where you can do quantum key distribution over 5 centimeters. This was actually was built in '92 by the guys who actually came up with the theory itself for BB84. Okay, there's Bennett and Bassard, and their guys. So basically, you can see that they use a simple LED as a light source. Okay, then they have a filter. Okay, and what they do is they filter down a very classical light source. It sends out millions and millions of photons, and what you do is you filter it down. You put lots and lots of filters such that in any single time interval when you're trying to detect for photons, there's only on average 1 photon inside that time interval. So that's how the standard way of trying to build a single photon light source. Okay, so that comes to our first way to try and attack this BB84 protocol. Okay, now remember what I said, the standard way to try and build this single photon source is to use a classical light source, which is very bright, and then you put lots and lots of filters. Okay, but this is actually a statistical method of trying to get single photon sources. And for example, it's what the statistics is described by a Poissonian distribution. And what happens is that most of the time, maybe 90% of the time, okay, you have 0 photons inside that time interval. But maybe 9% of the time, you'll have a single photon. But the remainder of the time, you're going to have 2 photons or 3 photons or 4 photons. Okay, so what happens in the cases when you have 2 or more photons, that an eavesdropper can actually put a beam splitter, okay, and try and split off some of the photons which are in the polarization state that you prepared. And in that way, she can actually know exactly what was the polarization state that Alice had tried to send to Bob. Okay, so why do people use this method is that it's much easier to prepare single photons in this way, because right now there's a lot of experimental work going to trying to prepare real single photon sources, and that's not so simple. So the first way you can try and hack a BB84 system, okay, is just by a simple photon number splitting attack. Okay, so BB84 using this method has a potential to be insecure. Okay, now the other technical detail about the BB84 source I showed to you was that, remember I said that you needed random number generators, okay, to try and decide whether to encode the photons in the horizontal or vertical, or in the plus and minus 45 polarization states. Now it turns out that you don't have to use a single classical light bright source to do that. You can also use small diode lasers. Okay. Now nowadays diode lasers are quite cheap and easily available. And the nice thing about diode lasers is that they come out with a very well-defined linear polarization state. So simply by rotating the output, by simply rotating your diode, okay, you can get the light coming out to be either horizontal, and then you physically rotate the diode, it becomes plus 45, then it becomes horizontal, and it becomes minus 45. So you can get all 4 polarization states just by rotating the diode. And so what people now do sometimes is that they buy 4 diodes, and then they orient them in the 4 different polarization directions that they want. And then what they do is they pass it through spatial filters, such that the light coming out from all 4 diodes have the same mode, okay? And then they transmit it across to Bob. So Alice will have 4 diodes, okay? And then she just has to randomly decide which of the diodes she's gonna select and send the light over to Bob. So that cuts down some of the need for random number generators. Okay, so on this side, there is now the method to cut down 1 random number generator. Okay, but on the other side, for Bob, one other simple way to cut down the random number generator is use a passive element. Okay, it's called a 50-50 beam splitter. Now, the beam splitters I talked about just now were polarizing beam splitters. So depending on the polarization state of your photon, it's either transmitted or reflected. But you can use a different type of beam splitter, which is polarization insensitive, so that no matter what polarization or state of the photon, it has a 50-50 chance of being transmitted or reflected. Now, in that case, what happens is that half the photons will be transmitted to another PBS, where you measure in horizontal and vertical. And in the other half of the cases, you send the photons into a measurement setup that prepares the plus and minus 45 polarization state. Okay, now the thing about this system is that it's quite robust, and people have actually done long distance quantum key distribution in this way. This is a result from 2002, where some guys put, now I can't remember which side Alice was. I think Alice was at the mountaintop and Bob was in the valley. And they managed to send single photons, okay, across 23 kilometers, and they could actually reconstruct an encryption key. So some of the latest developments in this field was that people are trying to think that you can do quantum key distribution between Earth stations and a satellite. Okay, so there's an interest in trying to go to longer and longer distances. I think that the latest result, record for distance was about 144 kilometer demonstration between two islands, okay, in the Atlantic. Okay, then there was the other way to try and improve your quantum key distribution method is to go to larger and larger bit rates, okay, and which was done by guys at NIST, okay, and they have megabit per second key exchange, okay. So that's the two of the so-called benchmarks for quantum key distribution nowadays. Okay, now let's take a break from there and let's talk about another way to try and attack quantum key distribution. Remember that I said that one of the nice ways to implement the 4 polarization states was to choose 4 single diodes and just rotate the polarization, just to physically rotate them so that the light coming out of different polarizations. Now it turns out that there's a flaw in this method, okay, simply because laser diodes are not identical. They do not give you the same spectrum no matter how you try to control the manufacturing process, okay? So in any particular batch that you choose, okay, they're gonna have slightly different optical spectrum. And what you're seeing here is a measurement on the optical spectrum of 4 laser diodes, which is used in a quantum key distribution experiment. And you can see that the peaks, okay, are all slightly different. So you could imagine an attack where the eavesdropper doesn't try and measure the polarization state, but simply send the single photons that Alice is sending to Bob, just to send them into a spectrometer, okay? And then just by seeing where did that photon lands up in the spectrometer, she can actually tell what was the polarization state of the photon. Okay, that's a good question. Now the thing is, no, that's a very good question, but it's not exactly right. First of all, you got to think what a photon actually is, okay? A photon is simply excitation of the electromagnetic field, okay? Now, you're not trying to measure something like a polarization state of the photon, in which case I agree you would need an ensemble. But if you're talking about wavelengths, okay, then the photon will actually obey the same, it will have the same frequency as it is in the classical field. And you can actually send single photons into a spectrometer, and as long as you're using single photon detectors, okay, you can actually pick up the direction in which the photon goes. Yeah?
But the photon also has a distinct frequency. One frequency and one wavelength. So how do you identify, distinguish between 4 lasers based on single photon measurements?
Okay, what you try and distinguish is actually remember when I showed you the graph just now, let's go back and have a look at the graph. Okay, if you look carefully at the graph, right, the peaks are different. Okay, so you can try and from the peaks you can actually tell statistically what's the proportion. Okay.
So you need a proportion of photons to distinguish.
No, you can use a single photon. Yeah, use a single photon. You see where it ends up on the spectrometer. Okay, and then from there you can tell the probability of which polarization from which laser diode was emitted. Yeah.
You read like more photons, not just one transmission. You can calibrate your.
Of course, the spectrometers have to be calibrated in the first place. Yeah. Okay. Where were we? Let's see. I was here. Oh yeah, I was here. Okay. Okay. Now we've just shown that BB84 has some technical problems about security and all that. But then if you implement it correctly, you know, if you have this spectral attack that I was talking about, you can actually correct for that quite trivially. You can put a bandwidth filter which only transmits the same amount of light from all laser diodes. But the bigger problem for BB84, which is a prepare and send protocol, is that you need a very large number of a very large set of random numbers, okay, continuously. Because remember that what you're trying to do is you're trying to filter down this laser diode that you have such that most of the time there's only a single photon inside the time interval when you're detecting photons. So that means that most of the random numbers that you are generating and putting into your system to decide your polarization states or your measurement outcomes, most of the time those random numbers are not being used to generate any key because most of the bins will have to be zero. They have no photons inside. So the question is, do you trust your random numbers? Okay, I mean, where are you going to get a high bandwidth source of random numbers? Now, it turns out that this is quite interesting because you can actually use a very special physical state to get around this problem, which I'll talk about later. But this is just to keep in mind that one of the problems is where do you get a large source of random numbers? Okay, so let's talk about quantum key distribution in the second way. So the first way using trusted couriers is BB84, okay, where Alice encodes information into single photons and sends it to Bob. But are there ways where you can encode the information into tamper-safe devices, okay, such that Alice and Bob can get the key and they have correlations from these tamper-safe devices? It turns out that, yes, there is such a system. There is such tamper-safe devices available, and they employ a concept in physics called entanglement, okay? Now, entanglement is actually something quite complicated. I'll try and walk you guys through what entanglement means, because even within the physics community, there's a huge debate of what entanglement actually is and how you can measure and all that. But the easiest way I can think of to describe entanglement is consider a joint system composed of two parts, okay? Now, the thing is these two parts are described by a joint state, okay, a joint quantum state. Now, if you take the two parts far away from each other, okay, and you try and describe one part by itself, then it turns out that it has no structure. You cannot really say anything in particular about that part. So imagine you have a pair of photons, for example, in a joint state, okay? Then you take A and B far apart from each other. Then you try and measure out the polarization state of photon A. And you will find that the polarization state of photon A, okay, is always in a mixed state. It has no well-defined polarization state. And then you look at B, and you measure out the polarization state of photon B, and you find that, again, there is no well-defined polarization state. So what happens now is you look at the measurement on polarization A, condition on polarization B, then you can find that there are correlations in the polarization state. For example, if photon A is horizontally polarized, then photon B is always vertically polarized, and vice versa. So that's what we mean by an entangled system. It's strictly a quantum effect, okay? There are no there's no classical model to describe the system, okay? And the nice thing about it is that you can actually build such systems in practice. Okay, how do we do it? Well, this I'm showing you a diagram based on nonlinear optics, okay, which is actually called the Couillard-95 method of generating entangled photon pairs. And the nice thing about it is it's not only entangled, but it's entangled in the polarization states. Okay, remember in BB84, to get the polarization states, Alice had to really decide what polarization state she had to encode in the photon. But in this case, it comes out straight from the physics. So what you do is that you take some kind of nonlinear optical crystal like BBO. Okay, nonlinear optical crystals are the sort of things which is quite common in nonlinear physics or laser physics, where you try and do, you try and change the frequency of light. Some of you might be familiar with things like second harmonic generation. Okay, so what happens is you don't do second harmonic generation here, you do something called spontaneous parametric down conversion, which is the reverse. So what happens is that you take a pump beam, okay, which is well polarized, and you pump a nonlinear crystal. And out of the millions and millions of pump photons that you have, sometimes one of them will decay into 2 photons. Now these 2 photons are highly correlated, okay, not only in time, okay, but also they have to obey momentum and energy conservation. Now, what happens is that in this particular case, one of the photons is always horizontally polarized. You can call that the signal. And one of them is always vertically polarized. So you can call it the idler, okay? So for example, the photon which is coming out in this direction, okay, its twin photon is the one which is right at the top, okay, right about the pump. Now, those 2 photons are not in any kind of entangled state. You can describe them by a separable state, okay? So each of them have a well-defined state. You just look at this photon here, it is always in the horizontal polarization. You look at its twin, it's always in the vertical polarization. Now, the nice thing about the system is that there is a point where these photons overlap. Okay, these 2 emission rings, they overlap, such that if you look at the photons coming out in this direction, you know that the twin comes out here. But you were to measure the polarization state of the photon in this direction, you'll find that it's in a completely mixed state. It is neither horizontal nor vertical. Okay, you only get information on whether it was horizontal or vertical if you condition the measurement on this twin photon. So this is how we create this entangled state of photons here. Okay, so basically this is the equation where we try and express it. You can see that it's actually this is what we call a maximally entangled state. Okay, so it's if this is photon 1, this is photon 2. Okay, so when photon 1 is horizontal, photon 2 is always vertical, and vice versa. Okay, this is in the HV basis. The nice thing about the system is that it is also entangled in the plus minus 45 state. So that if one photon is in the plus 45, the other one's in the minus 45. Okay, so this is actually very nice because what I want to say is that Alice no longer has to actively encode a choice of polarization states. Just by collecting the photons coming out of the crystal, it's already random. There's no way to say that the photons coming out here are always in a fixed polarization state. It's already random. Okay, so in that sense, you make use of the physical properties of a system to encode your randomness. Okay, so how do we do it in practice? This is one of the gadgets that we have in the lab. Okay, we try and make it small enough such that we can carry it outside and do field experiments. Okay, just some numbers is that we use a 40 milliwatt blue laser diode, and we can get about 24,000 of these entangled pairs a second. Okay. Closer look at the system is, what we do is we have our blue laser diode on the lower deck, we shape the beam, and we send it up to the upper deck. On the upper deck, the nonlinear crystal is held in one of these holders. So when the blue photon, the pump beam falls on the crystal, your entangled pairs come out in the direction which is shown by the red lines. And then we collect them into single mode optical fibers. And then after that, processing of the polarization states of the photons is quite easy. Okay, so how do you do QKD photon pairs? So imagine you have photon pairs, a source of photon pairs in the center. Okay, one of them is sent to Alice and one of them is sent to Bob. Okay, and then again, you just do passive choice of measurement basis. So Alice can choose to measure in plus minus 45 or HV, same for Bob. And then they continue what happened in BB84, the public discussion of whether they chose the same basis. And then you do error correction and privacy amplification. Yes?
What's the reason for the polarization rotator? Is that what it is? The lambda or 2?
Yes, that's what it is. Okay, you want to measure it in the plus minus 45.
Right.
So what you do is you do a rotation on the polarization state, such that plus minus 45, it actually... Correct, because our PBS is only in the horizontal and vertical polarization. Okay. So, okay, basically that was the idea of how we did it. Now, one of the problems with this method is that we don't have any timing information. In BB84, Alice, she encodes the polarization states actively, and so she knows when she's sending photons. So she has timing information. And she can send this information over to Bob and say, look for photons at this time, at this time, at this time. Now, in the process that I just described, photon pairs are born randomly, okay? They're born at the same time, within 100 femtoseconds of each other, okay? But they're born randomly. So what happens is that there's a bit difficult, it's a bit tricky because Bob doesn't know when to expect photons. So his single photon detectors just go click, 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 but he doesn't know when to look for a coincidence, okay? So you can imagine that, how should I say it? You can imagine that at the beginning, the photon pairs are all, aligned with each other, but after transmitting like over tens of kilometers, one of them is delayed by a lot, okay? So what you have to do is you have to do time stamping on your photons. So on Alice's side, she timestamps the photons, and Bob also puts a timestamp on his photons, and then they have to actually compare this classical information, this timing information, okay, to try and get a coincidence. So that's what we mean by coincidence identification. So this is just a diagram of how we do it. We have a timestamp unit of about with accuracy of 125 picoseconds, and we need a reference clock, okay, to make sure that both Alice and Bob actually start out with the same time. Now these reference clocks are atomic clocks, okay, but it turns out that using these atomic clocks, we only need it for like the first 5 to 15 seconds, because once the software has found the initial coincidence, it can do software tracking quite well. Okay, so we don't really need the atomic clocks for much more. We just need it for the initialization stage. Well, this is just a basic diagram of the software that is used on both sides. Okay, now the reason why I'm bringing this up is that all this software that we use for our quantum key distribution is now open source. It's up on our website. So if anybody wants to see more detail how the coincidence detection is done, they're welcome to have a look at it. Okay, but I won't spend too much time on this slide unless there are specific questions. Okay, so this was just talking about how to find the coincidence between the photons which have been delayed by each other. Okay. Okay, so this is just a little bit about how the error correction and detection is done. So what happens is that, you know, in practice, you know, you send your single photons to light. Sometimes there's noise or the polarization states change, especially because, you know, we collect them into single mode fibers, and single mode fibers are actually, they're like optical elements which will rotate your polarization states. Okay, so the thing is, you can't actually distinguish between an innocent error caused by, you know, your single mode fibers rotating the polarization state from eavesdropping attempts. So you have to treat all these errors as presence of an eavesdropper. So what you do is you try and correct for the errors by, you know, discussing the parity. You divide the keys that you have into blocks, and then you discuss the parity of the blocks. Okay, now this is just to show you that based on the fraction of errors you measure out in your key, you can actually find and estimate the knowledge of an eavesdropper. Okay, so how we denote it is using this IAB. For example, that's just the mutual information between A, Alice, and B, Bob. And IEA is the mutual information between Eve and Alice, okay? And by looking at the error fraction, okay, you can actually work out the maximum theoretical mutual information that the eavesdropper will have with Alice and Bob, okay? And from there, you can decide how much privacy amplification you would like to perform. Okay, so privacy amplification, in case you don't know what it is, very simply, it's just that, you know, after error correction and all that, you have a string of random numbers, which you think, a string of random bits, which you think can be used as a key. But from your, you know, your error correction part, you found out that there's certain fraction of errors. So you suspect that Eve may know a few of the bits. Now, you don't have to know which exact bits that she has information on. You just have to know the fraction. And what you do is you multiply it with a random matrix, and then you get a final secure key. Now, this random matrix can be public knowledge. The eavesdropper may know its structure. But what you're doing is you're mixing what Eve doesn't know, okay, with what she knows. So in the end, in the final key, she still has to guess like whether that bit was a 0 or 1. And in that way, you're trying to compress and remove all the mutual information that Eve will have. Okay. So the thing is, looks easy in practice, but one of the problems with, I would say, with current QKD systems is that privacy amplification in this way has always been analyzed theoretically in an asymptotic limit. They assume that you're an infinite set of raw bits. But, you know, in practice, you don't. So the question is still open, I think, on what happens if you only have a finite set of raw keys and you know a certain fraction is known to Eve. And when you do this step of privacy amplification, is it still secure? So what is the minimum length of the key that you will need? Okay, so that's an open question, I think. So this is just a schematic of our system setup, okay? So this was the source of entangled photon pairs that we have. We collect it in the single mode fibers. We do measurement outcomes, okay? And this is on Alice's side. She does time stamping, and then she does classical communication with Bob. And there's a classical channel which we have of 1.5 kilometers. So this was our test range on campus. On this side is the transmitter, which is on the roof of the administration building. And on the other side is my supervisor's house. You can see the swimming pool over there. Okay, so we managed to send single photons, entangled single photons across 1.5 kilometers. And in the end, we did get a secure key out of it. I'll show you the results in a minute. There's a short, brief photo of our kind of setup. Our single photon detectors are in small modules you can hold in your hand. Okay, they're in here. They're actually placed inside these aluminum blocks. Okay, and why we put them in aluminum blocks is that we want to cool them down. But single photon detectors can be quite noisy, so you have to suppress the dark counts. And you just might be able to make out these little beam splitters here, which were the beam splitters that I was talking about. Our single photon receiving and transmission devices are just these telescopes, okay? So they're just simple optical telescopes. And what I'm showing you here is a diagram, okay, of the cross-section of the light coming out of the telescope. So you can see that it's about 76 millimeters in diameter. So the single photons that we are sending, right, there might be single quantum states, but they're actually not very small. Okay, you can think of them as flying pieces of paper flying through the air. Okay, so they have a 76 millimeter diameter. So this is the first graph on experimental results. Just to measure raw coincidences first, okay, without any secure key, we get about 2,500 per second. Okay, this is just the background count, which we call accidental coincidences. It goes click, click, click. You think you have a coincidence, but these are things which come from stray light, the noise in your detectors and all that. Okay, to suppress all these accidentals, we actually use interference filters. So this is a result of like the secure key after full error correction and privacy amplification. You get about 800 bits a second. Okay, so just some details, like for example, the error correction code is something called cascade. It's the one in the cascade algorithm. Okay, so why we think this is nice is just that a lot of the complexity in the system is not much more difficult than what you'll find inside a CD player, because a lot of it is based on solid state light sources. Okay, the other nice thing again to emphasize that you don't need random numbers in this particular case. Okay, is Ling shifting. The guy who did the programming for this was very proud of it, because all that classical communication for error correction and timing coincidence, you only needed to exchange about 15 to 20 bits per detection event. It's compact. Okay, it's free space. You don't have to go through fibers in our case. Sometimes you can implement it through optical fibers, but in our case, it's compact and you can install it in ad hoc situations. For example, we shipped a kit to the Chaos Computer Congress in Germany 3 weeks ago, and it was very nice because it worked straight out of the box. So you can ship it around and exchange a key over arbitrary distances and arbitrary locations. Yeah, and it runs reliably hands-off. It produces key continuously. One of the things I should say, let's go back to the last graph, is that you might be wondering, what are all these little dips here? This is because in Singapore, we get really heavy rainfall, okay? And so sometimes when there's heavy rainfall, you can't see the other side, so you can't send photons across. So the key rate just dropped, but it recovers after a while. Now the thing is, you'll see that from 6 to 8 a.m., things start to go bad, simply because right now, we're only operating at night. We can't operate during the day because our entangled photon pairs have too wide a bandwidth. So we can't use too narrow interference filters. Okay, we just have to live with that for now. So one of the nice things to do is whether we can build entangled pairs with a narrow bandwidth, then we can work throughout the day as well. So now the thing is, entangled pairs for QKD, is it really secure? Well, we're pretty sure that there's no spectral fingerprint in the photon pairs, okay? Because if they are, then the quality of the entanglement goes down and you can't really exchange a key. Now, we don't need any untrusted random number sources. But the problem is that, of course, there are always software bugs around in our software. One of the things to note is that there's a lot of timing information that's exchanged, to get coincidences. So there's good chance that you can be able to, you know, tell or derive some information on the key that you're sending. But you're invited to look at our software, find holes if you want. It's all on this website over here. Yeah. Okay, well, I guess that's all I want to say today, and thank you for your attention. So do you guys have any questions? Yes?
I noticed that you use NTP server somewhere in your system.
Yes, yes.
NTP is only known to have accuracy of milliseconds.
That's correct. Now, you see, the thing is, the NTP server is just to get okay, we do our software stuff all in little laptops. So the NTP server is just to make sure that the laptops start out at least with roughly the same time. Okay. The actual time stamping is done in a separate electronic unit, and the time initialization there is done using atomic clocks. So the NTP server is actually right now just to get the laptops that we're using to have roughly the same time. Then they can start processing it. Now, one thing I want to say is that we really would like to get rid of the atomic clocks, because I mentioned that it's only used for the first 5 to 10 seconds. And so atomic clocks are actually expensive devices, and you want to try and get rid of them if you can. So I don't know. I think the challenge is how right now it's open to everybody, I guess, is if you can look at the code and you can find a way to get really precise timing information from the coincidences. You find a way to do it. My supervisor says you can have the atomic clock. Yeah. That is a great question. It has come up before. The thing is, QKD, people who are interested in QKD are typically very paranoid, and they don't want to rely on an external timing device. I'm not so sure whether that's such a valid argument, because you can think that you initialize your clocks using GPS, and then you discard the keys that you get from there, but you have already established synchronous. You'll be synchronous, and then you can start finding a key. So yeah, GPS is one thing to try. Yeah.